Yep.
All right, yeah, thanks so much. Yeah, I'm Andy Friedman from MIT, and I'll be talking today about the multiverse, one of the most exciting and controversial ideas, perhaps in all of science. And the idea of other universes might sound like it's straight out of science fiction, but surprisingly, the multiverse today is actually a logical consequence of our best understood theories of nature. Doesn't mean that we can say for sure that we know that the multiverse exists, but we do know that we know enough already to say that we have to take these ideas seriously. So, I'll begin by giving a sort of broad overview of the multiverse, and then Brian would follow talking about some of the strongest observational evidence we have for believing this picture. And David Brin will follow by talking about more ideas about how human beings might fit into this picture. And I'll draw really heavily upon ideas from my MIT colleagues, Alan Guth and Max Tegmark. They're currently in another universe about 3,000 miles east of here. And recently I had a chance to talk at the AAS meeting in Boston in a special session entitled Multiverse Observation Theory on the same panel with these two guys. And the fact that, the biggest astronomy collection of scientists in the world is having sessions talking about the multiverse just kind of tells you that this topic is becoming more and more mainstream. So, it's great to be here at the Arthur C. Clarke Center, pretending there. And I actually only heard about this place a few months ago, but it's really cool that a center devoted to the exploration of the human imagination actually exists. And it makes you feel like you're kind of living in a science fiction novel. And I think that if either of these two gentlemen were around today, I think they'd get a kick out of some of these ideas, which are all about exploring the limits of the possible. So the question at stake is in some sense the biggest question we can conceive of. How big is the world? How far does reality extend? And to human beings living just a few centuries ago, the Earth as well seemed like it might as well have been infinite. And it's interesting that we kind of come full circle, and the modern theory of cosmology is very much consistent with us living in an infinite space of which we can only access a finite part. So one arc of this multiverse story is the so-called Copernican principle. It's the idea that human beings don't occupy a special preferred place in the universe. The way the story goes, we used to think the Earth was the center of the universe. Now we know it's not even the center of the solar system. The solar system is not the center of the galaxy. There are hundreds of billions of galaxies that we can see just in the part of the universe we can access, and other universes are just sort of the latest chapter in the story. But the Copernican principle can be taken a little bit too far. I certainly happen to believe that human beings and life itself is very important in the cosmic scheme. And other aliens aside, we are the only beings that we know of that can actually think about and talk about these kinds of things and ask about where we fit into it. So kind of an outline of the levels of the multiverse. These are categories which were conceived by Max Tegmark, which I think they're very useful. The first level kind of corresponds to regions just beyond what we can see, things beyond our cosmic horizons, things inside of black holes. Inflation, which Brian will talk more about in his talk, is a theory of the early universe, which might lead to a plenitude of other universes. And Brian will talk about some of the evidence for that. I'll talk about the many worlds as conceived of in quantum mechanics, and even universes with other laws of physics. So these categories are by no means exhaustive. There are dozens and dozens of different kinds of multiverses that levels that people will discuss, and David will hint at some of them. And at least because we actually have really strong evidence, indirect evidence, for level 1, the question is not, does the multiverse exist? The question is, how many levels are there, and how could we possibly test them? So, how far can we see? We have really strong evidence that our portion of the universe is about 13.8 billion years old. Right here we have the familiar baby picture of the universe from the microwave background, which was formed about 380,000 years after the Big Bang. And here we have images of the most distant galaxies ever observed by the Hubble Space Telescope. Every single splotch of light in this image is a galaxy. But since light travels at a finite speed, this means that a telescope is a time machine, because we're seeing light from these objects as it was when it left billions of years ago. And when this is combined with the finite age of the universe, you have an interesting phenomenon where there's a limit to how far we can see. There's basically a sphere around us that represents how far light can have traveled since the Big Bang. And the question, as far as the first level of the multiverse, is whether this observable part is all that there is, or is there something more? So it turns out that because of the expansion of the universe, and because we think the expansion is now accelerating, if something was to emit light right after the Big Bang and it was just arriving at us today, that object would now be actually about 46 billion light years away. This is the so-called particle horizon. And so that's how far away the limits of things are today. So if you take seriously the idea that maybe there's a galaxy 100 billion light years in that direction, if you think that that's a reasonable thing to extrapolate, then you're already talking about the first level of the multiverse. And so if this space is infinite, or at least very large compared to this region, there's no edge to space. It would be really weird if the universe just sort of stopped right at this particular particle horizon. Now there are other boundaries which are relevant because we think the universe is actually accelerating in its expansion.
Triple light.
If we think about how far a light signal could travel even in the infinite future, because of the acceleration of expansion, space can actually expand faster than light. This is actually allowed in relativity. It turns out that there are places that we can't reach, even if we traveled at the speed of light forever. These are beyond our so-called cosmic event horizon. And this is one of the reasons why I think it's fair to talk about these regions as other universes, because if acceleration continues, then these really are, if general relativity is correct, inaccessible in principle forever. So, just a little bit about inflation. So, the idea is we have an exponential period of expansion of space in the early universe, as illustrated here. It solves a number of problems in cosmology, which Brian will discuss a few of, and it makes a number of testable predictions. But it also predicts that space is much larger than the part that we can see. One of the ways we can look at this is by looking at, let's say the universe was curved. This is a two-dimensional analogy of actual three spatial dimensions in our universe. But the idea is that an exponential expansion of space kind of smooths out the curvature, makes any little local patch, any ripples of curvature flatten out. This is true for the same reason that any local patch of Earth, like a football field, looks flat, even though we know Earth is curved on a larger scale. So the radius of curvature of the universe, we can measure the curvature locally, and we can then put kind of a lower bound on this radius. And it could be infinite, but we also know that it's at least very large, much larger than the part we can see. So that's why inflation gives us really strong evidence. If anything that tests inflation is evidence indirectly for the level 1 multiverse. What do these other universes look like? We think they would have the same laws of physics, the same fundamental constants of nature, like the speed of light, mass of the electron, the parameters of cosmology, but we think they would have different initial conditions and therefore different outcomes. This is represented by these different baby pictures of the universe, and some look much different than others. And the evidence for CMB and inflation, from CMB for inflation, for a flat, smooth, tangibly infinite space, is the strongest kind of logical argument we have for this level of the multiverse. So there may be other regions that are practically next door that also include things beyond what we can see. These are, of course, black holes, which we have strong evidence that black holes exist at the center of basically every galaxy, and there are probably black holes, within a few hundred light years in our own galaxy. But we don't know really what goes on inside a black hole interior. We don't know, for example, if you jumped into a black hole, if you would be destroyed by a firewall of high-energy radiation as you cross the so-called event horizon of the black hole. We don't know if you'd be spaghettified into a long strand by the differential gravity of tides. You probably would for a small black hole, but for a large black hole, tides wouldn't be so bad. We don't know, for example, if some or even all black holes perhaps are wormholes. These theoretical objects in relativity which would connect at distant points in space-time. So, it could very well be that if you jumped into a black hole, maybe you'd actually survive and find yourself in some other portion of space-time, which would essentially be another universe. And this leads one to ask the question, are we perhaps actually already living inside of a black hole? This is not as crazy as it sounds, and people are actually seriously investigating, from a theoretical perspective, the duality between an expanding universe as seen from the inside and potentially a black hole as seen from the outside. I don't think that we know enough to be able to say anything really definitive about this picture. but it is an interesting kind of other conception of the multiverse. Some people have taken this idea really seriously, like Lee Smolin with his idea of cosmological natural selection, talking about black holes and baby universes reproducing. The ones which produce the most black holes win out in the Darwinian war. I think that particular theory is wrong in detail, but the idea of thinking about Darwinian processes on cosmological scales is very interesting. So, jumping back to inflation, it turns out that it's actually really hard to build models where inflation only happens once. So even if inflation happens in our region, stops, and then we have the normal kind of Big Bang evolution at a more leisurely pace for the last 13.8 billion years, inflation may very well be going on somewhere else. If you take this idea to the logical conclusion, there's no reason why this process would ever stop. So we have what we call eternal inflation. For each of these inflationary bubble universes, they are so far away that we could never travel to them even if we went at the speed of light forever. But they have a different character than anything we've talked about before, and they form the units of the second level of the multiverse. Another theoretical motivation for the second level of the multiverse comes from string theory, which is our leading candidate theory for quantum gravity, which would unify quantum mechanics, which covers physics at the small scales, and general relativity, which covers gravity at the largest scale. And the idea from string theory is that there may be more spatial dimensions than the familiar 3+1 space-time dimensions we're used to. We all found our way to this room at this specific time, so we're pretty good with the idea of 4 space-time dimensions. But there may be as many as 6 or 7 other ones. And one idea in string theory is that they're all sort of curled up and tiny. So if you zoomed into the space-time, you would see them. And they're represented here by these complicated mathematical shapes. Here's a movie of a kind of 2-dimensional cross-section of this potential 6 or 7-dimensional object. And the idea is that we now know that there are literally an astronomical number of different ways of mathematically constructing these spaces. So each of these corresponds to a different way that a universe can be. And in fact, we think that different ways of curling up the extra dimensions corresponds to different ways of having parameters of physics like the speed of light, or the mass of the electron, or the number of particle families, or even the cosmological parameters like the amount of dark energy governing acceleration. And the connection to inflation is that eternal inflation is the physical mechanism which would actually populate the landscape of all the potential solutions of physics, according to something like string theory. So, in a level 2 multiverse, what would these universes look like? They would have the same equations of physics. They'd still be governed by quantum mechanics, for example. But they would have different constants of nature, as mentioned. And so the evidence for this level is much more tenuous and indirect. But there's a sense in which all the evidence for inflation that we can gather with things we can really observe locally, logically extrapolated, point to this level too. If you accept the theoretical arguments that inflation is numerically eternal. And in addition, this level explains another mystery called fine-tuning, which I'll discuss. So, it turns out that if you look at things like the speed of light, the mass of the electron, actually the dimensionless constants of nature, which don't depend on which units you use, small changes to these parameters would probably make life as we know it impossible. So, for example, if the dark energy, which governs acceleration, is too high, the universe expands and accelerates so fast that galaxies never form. So if you believe that you need galaxies in order for observers like us to come to being, then that's bad news. And it's actually pretty easy to change the parameters around such that you have no stars, or atoms, or stable chemical elements, no periodic table, no chemistry. So if you have that, you kind of remove the crucial prerequisites for life as we know it. So why do we exist? Why are the knobs fine-tuned and kind of tuned just right for us to exist? Well, maybe we just got lucky. Maybe they were chosen by some force or some intelligence. Or maybe, if you have other universes with different values of these, then it makes it plausible and more likely, and maybe even inevitable, that at least one will be just right. This leads us into the very controversial idea, the so-called anthropic principle, which is the idea is that given the fact that we observe ourselves to exist, that's actually data, that's evidence, the physical constants must therefore allow for our existence. So if there's only a single universe, this is just a tautology, and it tells you nothing. But if the ensemble of universes exists, if you believe the indirect observational evidence and the theoretical reasoning for the second level of the multiverse, this argument is actually very logically sound. And here's another example which illustrates that. For example, it could be that the constants of nature are more like environmental selection sets. Like, for example, the distance of the Earth from the Sun. So, why is it that the distance of the Earth from the Sun is just right so that water can be liquid on the surface of the Earth? Are we surprised by this? The answer is, well, of course we're not surprised by this, because we know, especially now, that there are thousands and thousands, probably billions of other planetary systems, each of which have very, very different distances as a distribution of distances between stars and planets. And some of them are going to be the ones that are consistent with the things we need for life, and so of course we're going to find ourselves living in a place like that. And the logic is just exactly the same for the multiverse. So it really comes down to, do you believe the observational indirect evidence and theoretical evidence for this level? Just take this seriously. So switching gears, this is kind of what seems like a completely different level of the multiverse, the many worlds of quantum mechanics. This is the view that's percolated most into popular culture, the idea of parallel timelines, the idea that the universe splits. There's a quantum event. This is a film reel of Schrodinger's cat, who you might have heard of. And the idea is that nature would kind of take on this sort of branching structure to reality. And the equations of quantum mechanics would be interpreted to say that all the possible outcomes actually do occur somewhere. So what's the evidence for this? Well, some people already argue that the many worlds view allows us to tell the most coherent story about what's actually going on in things like the famous double-slit experiment, where you have phenomena like quantum interference. Some people also argue that quantum computers, when they're built and are able to perform calculations that seem impossible to do as fast with an equivalent classical computer, some people argue that the best way of interpreting what's going on here is that computations are actually being shared amongst different branches and different universes. Now the problem here is that there are dozens of interpretations of quantum mechanics. There are more of them by far than the number of different kinds of multiverses that people talk about. And essentially all the other interpretations give the same predictions as the many worlds interpretations. So we need a lot more. We need information from a new theory, probably from quantum gravity, that would give us a tiebreaker, that would allow us to actually experimentally distinguish between different interpretations of quantum mechanics. But it's still the case that the many worlds view is still consistent with everything we know. So we can't rule it out. So the most speculative level of the multiverse in Max's scheme is the multiverse that would allow for different laws of physics. And the idea is that these would be governed by different mathematical structures, as illustrated by these different mathematical shapes. And why would you take this seriously? Well, there's this interesting question about why math describes reality so well. Eugene Wigner, a Nobel laureate, called this the unreasonable effectiveness of mathematics and the physical sciences. And one answer, which this approach kind of adopts, is maybe it's because deep down reality really is fundamentally mathematical. Maybe math is the fundamental wellspring of existence. Now, it's very hard to understand, how that would work, and this is extremely speculative and philosophical, but there are a lot of people, including Mad Max, who take this very seriously. So, is this science, or is it just philosophy? And it's not an understatement to say that there are huge skeptics of the multiverse, and that these ideas kind of represent a battle over the soul of science in theoretical physics. Skeptics say that if we go down this rabbit hole, it's the end of science as we know it. We'll never be able to make predictions. How in the world can we possibly test these things? These regions which appear to be inaccessible in principle forever. Anything goes, and so we might as well give up. So I think this is a little bit alarmist. And I actually view the situation as a challenge and an opportunity to try to think of new and clever ways to test these kinds of ideas. If you say that something will never be testable in principle, what you're saying is essentially that you, yourself, can predict the entire future history of science. And I think that's a little bit too strong of a claim. And so one other thing that's important to remember is that parallel universes themselves are not a theory. They're predictions of specific theories, like inflation. And eventually, perhaps, we'll be able to make predictions from string theory. It might take decades, but nobody knows how long it'll take to test a given theory. Nobody has the ability to predict the future. And if you want to give evidence for a theory, you don't need to test all of its predictions. You just need to test some of them. So, inflation, for example, has a whole bunch of predictions that we can test locally. You know, and many of you guys in this room work on these kinds of things. But if you take the logical consequences of inflation seriously, it also predicts the existence of these other regions we can't directly observe yet. Maybe never. Maybe you'll find a clever way to do so somehow. But the idea is that you got to take all the predictions of a theory seriously, even ones you can't test yet today. You can't just pick and choose. Science is a coherent whole. And maybe there are better theories that won't make those predictions. That's what some people hope who are trying to come up with alternatives to inflation and alternatives to the multiverse. So overall, some people still hate the multiverse. But fewer people are just dismissing the idea because they say it's crazy. And kind of in summary, if you accept that the part of the universe we can see is not all that there is, and I think this is the standard view, uncontroversial view of modern cosmology, then you already accept at least the first level. If you accept the logical extrapolations of our best physical theories, like from string theory and from inflation, internal inflation, if you accept that the fine-tuning is a mystery which needs explanation, and this is the best answer we've come up with so far, then you have reason to take seriously level 2. If you think that the many worlds view gives the best explanation of quantum phenomena, then you'll take seriously that level. And if you think math is discovered, it's not invented, and the reason is because the world actually just is fundamentally mathematical, then you'll take seriously this other level. And I think overall that if we want to dismiss certain ideas based on just aesthetic judgments, that's fine, but we should be honest about it. And I will admit that I think these ideas are very cool, but instead of just saying that I believe them with certainty, I certainly don't believe these with certainty, I say, okay, well, they're interesting. How can we figure out how to test them? How can we figure out clever new experiments that we can do locally that might allow us to make more sense of this picture? Maybe there are things that, connections we haven't discovered that would allow us to do local tests which actually give us access to these things which seem perhaps very far away. Quantum gravity has some really interesting suggestions. It could be that things which naively look very, very far away according to general relativity might actually be in some sense really close to us in quantum gravity. And if that's the case, our ideas about how far away some of these places are might be a little bit in need of revision. Space and time itself might not even be fundamental in quantum gravity. So there may be experimental paths, and we shouldn't close the door prematurely. And overall, it's from my perspective, it's a really fun and exciting time to be a scientist thinking about these things, certainly at least in this universe. Thanks.
Brian, you want me to keep recording for the questions, or?
Yeah.
Yeah, so like 3 minutes over?
Yeah, about 3 minutes.
Yeah.
Okay, yeah.
Einstein died in 1955, not in 1995.
Yeah.
Yes, this is the universe where the typo
And you had
existed.
also two words, I mean the same word twice on the next experiment.
Okay.
Yeah, I have notes. I have notes.
Okay, yeah, absolutely. I'll
I
go
think
ahead.
the previous one.
I'll go ahead and fix that. Yeah, thank you.
So does that mean that extra dimensions would be a type of multiverse, or extra dimensions? Because like, is it just that we live in a universe that contains all those dimensions, we just don't access those other dimensions? I don't know. I don't know how that's seen in the multiverse world.
Yeah, that's a great question, and I think that the second level of the multiverse broadly encompasses ideas about extra dimensions. So in string theory, I only really talk about curled up small extra dimensions, but there's ideas that perhaps there are very large extra dimensions, maybe infinitely large, maybe curved, and perhaps the 3+1 dimensional space that we inhabit is embedded in a larger space, and maybe these universes can even interact, maybe they can collide. One alternative to inflation is the so-called brain world model, where brains, which are these higher dimensional objects, collide, and that gives you the Big Bang, it can reproduce some of the features of inflation. One of the problems is that these models don't predict gravity waves. So the bicep results, if they hold up, are really kind of bad news for those alternative theories. But people should definitely come up with these alternative ideas. And some will seriously they're trying to explain the mystery of dark matter. The idea of matter which appears to be interacting gravitationally but doesn't emit light. We can only detect it indirectly. There's some serious ideas to think about in a brain world scenario, dark matter as being due to the gravitational influence of a nearby brain. And the interesting thing about these ideas, especially the cyclic brain models, is that they were designed in order to get around the implications of inflation and internal inflation, which give you this multiverse. So the people who designed them hate the multiverse. And it turns out that, as I view it, and Alan Guth agrees with me, that those models produce a multiverse of a different kind too, kind of a temporal multiverse, where you just have different cycles. In each cycle, the cosmological parameters and the physical constants can be different. And so, extra-dimensional scenarios like that, they all kind of fit into the level 2 multiverse scheme.
So the quantum computing, where we launch a bunch of parallel universes to do our jobs, I mean, that makes perfect sense if you have no problem going crazy. But if you, how do you share now? I mean, you're saying that like the double slit experiment is saying, all right, we've got 2 different universes that are now sharing. I mean, the branching I understand, but the sharing I'm having a problem with.
So the double slit experiment, it's this idea that if you have a stream of photons, and there are 2 possible slits they can go through, they form this wave interference pattern, but if you actually try to measure which slit things you're going through, you can rapidly destroy the interference pattern. But when you do this experiment with single photons, like one at a time, like 1 photon every second, kind of a slow rate, the interference pattern slowly builds up. And if you're trying to tell a story about what's going on, like, is a single photon itself going through both slits? According to some ideas like those of David Deutsch, the best explanation for this is that photon is interfering with what look like shadow photons that we can't access. These would be photons effectively in other universes. And basically, his argument is that these photons are behaving as if they're interacting with these other unseen partners, and that explains the phenomenon. So we should take these unseen partners seriously. Not everybody buys that argument. But the idea is that if you believe that quantum computing is best described in this framework of computations being shared amongst universes, you're also believing that the universes are not completely parallel, that they really can interact in interesting ways, and that there are limits to what we can do, but that they can do things. It's an open question whether they can perform completely different kinds of computations than just classical computation. But it's pretty universally agreed that they'll be able to do things faster. And then people ask the question, where was the computation performed? Where are the resources? And you might not think that's the right question to ask, but that's the reason why people take seriously the idea of, well, it must be performed somewhere. Hard to see how the resources exist here. Maybe they exist somewhere else.
Just wanted to say that the phasing, phase 1, 2, 4, is somewhat misleading because there is a fundamental difference between phase 1 and all the rest.
Yeah.
Because you're going from particle to event horizon. So, the presentation is, if people are not aware of that can be easily, I see the purpose of the way describing it in these 4 phases, but I would claim that the first phase has nothing to do with multiverse. Well, although I understand, as I say, that it builds up the reasonability of having, of the possibility of going from phase 1 to phase 2 and the rest.
I certainly take your point. I think that anytime you're trying to come up with definitions and classification schemes, there are going to be points of disagreement, and I think that's a reasonable concern. I do think, though, that there are all sorts of approaches, especially approaches that try to unify at least the first three levels, kind of in a cosmological context, that would kind of unify the many worlds into one. Like we're really talking about one large space, even in eternal inflation. Absolutely, like when you're talking about particle horizons and event horizons, you need to be specific. But even for this level, where you know the particle horizon currently is actually larger than the event horizon. The event horizon, like galaxies at redshift 1.8, are living on the event horizon right now, and you know we routinely observe them all the time, but we couldn't send a signal there, even if that signal went at the speed of light forever. So if you believe that stuff exists beyond that, and if you believe that the acceleration will continue, then I think it's fair to call those other regions effectively parallel universes. They're causally disconnected. So that's the motivation, and they're causally disconnected almost in the same way that the level 2 bubbles are, because you know acceleration today is very similar to inflation in the early universe, just at a smaller scale. So fundamentally, you're talking about space expanding faster than light, and that's the reason why these universes are parallel, at least if you believe classical general relativity describes the situation. But I certainly take your point. I mean, if you read Brian Greene's book, The Hidden Reality, he's got 9 different universes in his classification scheme. And when Brian and David and I were brainstorming, we came up with 20 or 30, and that any classification schemes have limits. But I really just kind of wanted to follow Max's, because I think that it's the one that it's at least the clearest that I've seen.
I want to say something controversial, maybe.
Sure.
I think we are impatient. I think someday somebody will write down a theory from which you can calculate the mass of the electron. And we will look silly, afterwards, having thought that because we cannot calculate the mass of the electron, it must be a random number. And therefore it's made in many different values in many different universes. They'll say we were impatient. We did not know the physics law that gets me the mass of the electron, and we invent all these things. We shouldn't do that. People have been doing that for centuries and thousands of years. They invent gods and they invent all kinds of things, to explain the world at their instant in time that they are alive. Our instant in time that we are alive right now is completely insignificant. We all agree about that. Our place is insignificant, our instant in time is insignificant, we are insignificant.
But that's what makes us significant.
It's a very pretentious thing to say, because we can't calculate the mass of the electron, it must be a random number, and created many times in different values, We have to be just wait a bit.
I think that's a reasonable criticism, and certainly the goal of string theory initially, and the goal of extending particle physics was to come up with theory which would do exactly what you're proposing. And you're correct, we could be being impatient in the sense that just because in the past 3 decades we haven't been able to do it, doesn't mean that we will never be able to.
Right.
So I think people should continue trying to do that, trying to come up with a theory. And at the very least, there's dozens of parameters in this list of fundamental parameters and cosmological parameters. I would not be surprised if further understanding reduces that number. But personally, I think it would be really, really difficult to come up with a theory that is unique, where there's no other possibilities. It's just the only logical one that works, that is going to give us these values from first principles. Now, this is admittedly an aesthetic bias. And I think it's the same kind of aesthetic bias as the idea that maybe you believe that the universe would be simpler, more beautiful if we did have that theory that gave us these values of the parameters. I just think that the jury is still out, and we're going to we're going to learn more as things go on, but I don't think that the argument that you pose means that we shouldn't explore this other avenue too. I don't think that it's the end of science as we know it. I don't know if you would go that far either, but I think that there